We now have the next speaker, Professor Ozaktas. So thank you very much for you to be patiently waiting. If you want to upload your slides, I can take the opportunity to introduce you as well. So we have Professor Ozaktas, who's a member of the Turkish Academy of Science, IEEE Fellow, SPIE Fellow, OSA Fellow. He's a professor, Department of Electrical Engineering, Belkent University. He's a recipient of the TUBI-TAK Science Award, and he's also an ICO Prize and Ernst Abel Medal recipient. Okay, so without further ado, I'm going to give the floor to Professor Ozaktas to give his talk on the story of optics in computing.
Okay, can you see my slides?
I can. Thank you.
Okay, thank you. Okay, hi, I'm Haldun Ozaktas, and I'd like to give you a quick and intense overview on the story of optics in computing. Now, if we think of the key areas of information technology, like, communication, storage, sensing, display, manufacturing, in all of them, optics is widely used. But it is not as widespread used in processing, at least in general purpose computing. So some believe optics will likewise find more widespread use in the processing of information in general purpose computing. And how far this will go is controversial, but many agree that optics will play an increasing role in electronic computers, possibly together with electronics in a complementary manner. That's why in the title of my talk, I especially chose the word optics in computing rather than optical computing to emphasize the role may be complementary rather than central. Now, we want to distinguish between different kinds of optical processing. There's analog optical information processing, there's digital optical computing, there's optical interconnections and optoelectronic computers, and then there are a bunch of emerging or novel uses. Now, first, we might talk about analog optical information processing. This is basically based on the fact that plane waves making different angles correspond to different frequencies. So plane waves with smaller angles with respect to the optical axis correspond to smaller frequencies, and plane waves with higher angles correspond to higher frequencies. This means that there's a direct correspondence between Fourier expansion, the common Fourier expansion into different frequencies, and the expansion into plane waves. The one-to-one correspondence between expansion of light into plane waves and expansion of signals into Fourier components. Looking at this system here, once the frequencies have been coded into the angles of plane waves, it becomes possible to easily filter images as desired. In this system, there's an input plane where we have some image. And this lens will direct the different frequencies, because they're coded into different angle plane waves. It will direct the different frequencies in different directions, and they will fall on this central plane. And on the central plane, you will observe the Fourier transform of the image. That's all it takes to take optical transform. You just need a lens, and you will observe a transform here. And once you have the Fourier transform here, it's an easy matter to filter it. If you want a low-pass filter, just cut out the center of a piece of paper and put it here, and the low frequencies will pass and high frequencies will be blocked. And you can do all sorts of sophisticated filters by introducing custom transparencies here. And then the second part will do the inverse Fourier transform, and you can process huge resolution pixel images in just the time it takes light to propagate from here to here. It's almost too good to be true, but there's a catch. And the catch is that this is an analog system. So if this is not the only operation you're going to do, and you're going to do you're going to follow this up with consequent steps, then of course noises become a limiting factor. Now, these fundamentals were known from very early times, and there were elementary applications, but there was one problem. These operations required coherent light, and coherent light sources were very, very hard. You'd have to use like an arc lamp or something like that, and it was far from practical. Then the laser came along, and laser suddenly solved that problem in the best possible way. And there was a renaissance of very clever systems that could solve problems involving large data that the digital computers at the time could not solve. Right? These were problems in areas like synthetic aperture radar, pattern recognition, holography, and things like that. And the computers of the 60s couldn't handle the huge data involved with them. So these represented significant success for optical processing during those times. And these matured throughout the 70s, and very high resolution images and large matrices could be processed in parallel, again, in just in the time that it takes for light to travel from one end of the system to the other. An example of that would be, for instance, this matrix vector product architecture. Looking at, you can almost see how the matrix is multiplied, right? There's a vector, and the elements are spread out onto the elements of the matrix. They're multiplied there, and they're collected back in the transpose direction to the first. So you can almost see how the matrix is multiplied by looking at this diagram. And then there were other things. For instance, a lot of interest was in hybrid computer-controlled systems. This was one of the first ideas that tried to combine the weakness, tried to complement the weaknesses and strengths of optical and electronic systems. Now, I said, optical systems can provide a very large number of three-dimensional interconnections and global connections, something that is very difficult, well, at least at the time, for electronic systems to provide, but it suffered from noise because it's an analog system. And in here, both optics and electronics are in the loop, right? So the optics can provide the massive matrix multiplications and the massive image filtering operations, but there's also electronics in the loop. So that electronics can refresh the signal values, amplify or refresh the signal values, and eliminate the problem caused by accumulation of noise. So so a lot of such systems were considered at the time. Throughout the 80s, there was some stagnation in this area, mostly because digital computers started to get processing powers of such a degree that you wouldn't bother trying to build an analog or hybrid system anymore, because you could program anything on your PC, and computers got so powerful that kind of made many of the past successful optical systems redundant. So interest turned in some other directions, such as digital optics and optical interconnections. With digital optics, I mean the idea of a computer that is totally optical means that the switches are optical, the gates are optical, and also the interconnections are optical. Sometimes the word all optical computing is used to distinguish this. Okay, so this is one schematic of an example of the many. There were countless proposals, but this I think is quite archetypical. So basically we have optical logic, optical gates, optical switches. Okay, and there's a large array of optical switches, like a two-dimensional array of optical switches, and also these are fed into some optical interconnection unit. This contains lenses and prisms and holographic elements and diffractive elements and all kinds of stuff, which can provide a global pattern of interconnections from this plane back onto itself, and then again you switch and then go. So you could build a sequential logic system or finite state machine in this manner. Other proposals, there were many other clever things. I can only mention a few of them. For instance, this was a smart system. It was basically the logic operations in this one were implemented by overlapping shadows, right? There wasn't actually any switching going on. This overlapping shadows would create the optical, the desired logic circuit was created by overlapping shadows. There was also a lot of interest in telecommunication switching networks, optics for telecommunication switching networks, which was natural because the signals are optical, and when you want to, they're going through optical fibers, and when you want to switch them, turning them to electrical signals, then switching them, like in a telephone exchange, and relaunching optical signals is kind of doesn't make sense. I mean, if you can make the switches optical as well, the light signals can just fly through the system without ever having to be converted to electricity. It would be like a transparent switching system, and the light would just be routed. And there were actually some quite successful demonstrations that this could work. However, none of these developments became mainstream. One reason was surely that there was too much investment in the electronic approaches in many ways, and it was difficult. And the other was that the advances in digital electronic computers often kept electrons always one step ahead. There was a lot of discussions. There was endless arguments at the time about the reasons why these did not succeed and become mainstream despite their apparent promise. I mean, people used to draw diagrams like this. Probably you can't read this, but that power versus switching time, and you would put various different technologies and optics and semiconductors and superconductors in different places of this diagram and argue over the thermal limits and quantum limits and things. You would argue why one technology failed and one technology succeeded. And there were lots of variations of this. For instance, this is another, like the density rate, data rate, and there would be like limits, loss limits, and speed limits, and thermal limits, and things like that. And you would argue why one technology is superior to the other. But these debates, in a sense, never ended. They just dissipated. And but as these debates continued, parallel development occurred during those times. In electronic computers, interconnections had started to consume more space, energy, and delay than the devices in the computers, and they were starting to become the bottleneck. And as a result of this, of these problems, optical interconnections were proposed as a solution. Most of these problems were due to electrical resistance, and optical interconnections do not require conductors because of their high frequency. And already optical communication was already being used for long distance communication and was being used for shorter and shorter distances. So there was some merit to the idea that if this trend continues, they would eventually inside computers. From a fundamental perspective, it seemed optics could solve most of the problems of electrical interconnections: resistance, capacitance, matching problems, the consumption of a lot of space and energy, crosstalk, routing problems. And superconductors could only eliminate some of these, and optics would be capable of eliminating a lot of these problems. And furthermore, it could provide three-dimensional circuits and parallel structures. And people try to estimate to what distance down optical interconnections can go. And the estimates made in the 90s predicted that they could go down to at least 1 centimeter. That interconnections as short as 1 centimeter should be made optically, and then electrical connections be used for shorter ones. For instance, this was some of the kind of envisioned ideas. You would have sources on detectors on your VLSI circuits, and there would be a holographic routing element, and that you would be able to make a jump from one point to the other, avoiding without having to spend a lot of real estate for the long distance connections on the chip. Switching back to analog information processing for a moment, the 90s brought a revival with the fractional Fourier transform. The fractional Fourier transform, just a quick review if you've never heard of it. This is a rectangle function, and this is the sinc function, which is the Fourier transform of the rectangle function. And here I have the 0.25, 0.5, 0.75 fractional Fourier transforms, right? So the fractional Fourier transform is the fractional power of the Fourier transform operator, right? So it interpolates between the rectangle and the sinc function as the order parameter, fractional order parameter goes from 0 to 1. You go from the rectangle to the sinc. I try to show that here in 3 dimensions as well. The axis from -4 to, I don't know if you see my pointer, but the axis going from -4 to 4 shows a rectangle, and as you change the fractional order from 0 to 1, you can see that it evolves to a sinc. And the fractional transform is also shown to be closely related to time and space frequency distributions corresponding to arbitrary rotations and phase space. And the relation to optics was that it was shown that propagation through an optical system like this one, there are filters and lenses, this could be like some compound optical instrument with many lenses and filters. And so it was shown that propagation through an optical system of this kind was an act of gradual and continual fractional Fourier transformation, where the image cycled through image and Fourier transform planes following a continually increasing fractional order. So you would start with 0, 0.1, 0.2. The image would be fractional Fourier transformed as it goes along. And this led to the concept of filtering in multiple fractional Fourier domains. So like normally when you do Fourier domain filtering, you just go to the Fourier domain, apply a filter, and then go back. That's all. Whereas here, you can go to the 0.3 domain, apply a filter, then you go to the 0.8 domain, apply a filter, go to the 1.3 domain, apply a filter. You can go to as many different fractional domains as you want to apply filters, and this gives a lot of degrees of freedom and vastly more flexibility, showing improved performance. Another area that optics received a lot of interest was optical neural networks, which were suggested quite a long time ago, actually, and some prototypes were built. The main idea behind this is that neural networks have a lot of connections, and these connections are a lot of crisscrossing connections. All ideas have a lot of connections, and these connections are far-reaching connections. You don't just connect to your nearest neighbor, right? So and electrically, this is more difficult to provide. Whereas with optics, light beams can cross through each other, and you can have three-dimensional architectures. And so optics can efficiently route the dense pattern of global interconnections of neural networks in 3 dimensions. So coming down to the turn of the millennium, optical information processing had reached a certain level of maturity. And despite never playing a mainstream role in general purpose computing, its legacy continues in a large diversity of areas that are too much to review or even mention in this presentation. So I'll have to satisfy myself with a random sampling. One of the most natural application areas is the capture and display of visual information, of course, where we are increasingly seeing a merger of optical and computational parts, optical and digital parts, to be designed in a mutual aware manner. So it's not like the optics is separate and the computation is separate. They are being designed to take advantage of each other. Different kinds of displays involve heavily optical processing, laser-based, MEMS-based, near-eye, head-worn, light field, virtual reality displays. Meta lenses are lenses based on nanotechnology, manufactured at small scales with nanotechnology approaches. Three-dimensional television and video has been in, there are different approaches to this: stereoscopy, integral imaging, holography, and these have been studied. These are still receiving continued interest. And of course, on a separate note, computational imaging is probably a perfect example of the integration of optical and digital processing that is now quite widespread. There are a lot of other areas that I can just barely mention. They include nanoscale photonic processing systems, systems for biological, medical, processing systems for biological, medical sensing and communication applications. And of course, quantum optical information processing continues to be something whose promise is to be upheld in the future, we hope. So thank you for your attention. And those of you who are interested can learn more and find a large number of references in this review paper.
Brilliant. Thank you very much. Like I said before, any questions, put it into the chat. And also, if you can put your email address in the chat as well, so people can reach out to you. Yeah, thank you.